What if a tiny material, only a few atoms thick, could make quantum computers arrive years earlier than anyone expected? Microsoft claims its latest quantum chip improved qubit lifetime by nearly 1,000 times in just 12 months, a jump that would normally take almost 10 years at the industry's usual pace. If these results hold up, the biggest race in computing may have just entered a completely different league. Today's fastest supercomputers perform over 1 quintillion calculations per second, yet some problems would still take thousands of years to solve. Quantum computers use qubits and superposition to process many possibilities at once, making them promising for AI, medicine, battery research, and cybersecurity, with trillions of dollars at stake. The biggest challenge is keeping qubits stable, as heat, vibration, and radiation can destroy them within milliseconds through decoherence. To prevent this, quantum chips operate inside refrigerators at 50 millikelvin, nearly 50 times colder than deep space. Even under these extreme conditions, many qubits still fail almost instantly, making stability the industry's biggest obstacle. Every phone, laptop, and gaming PC runs on bits, where every transistor is either 0 or 1. Qubits completely ignore those rules. Thanks to superposition, they can exist in multiple states at the same time, while entanglement allows different qubits to become deeply connected even when separated. Instead of testing one solution after another, quantum computers can explore huge numbers of possibilities simultaneously. They are not faster at everything, but for certain problems, they could outperform today's most powerful supercomputers by an enormous margin. Most quantum companies focused on improving existing technologies. Microsoft went in the opposite direction. More than 20 years ago, it started building topological qubits, a completely different approach that stores quantum information across an entire structure instead of one fragile point. The concept was first proposed in 1997, and Microsoft officially committed to it around 2004, after mathematician Michael Friedman convinced Bill Gates that this could become the safest path toward fault-tolerant quantum computing. It was an incredibly risky decision that many believed would never work. Microsoft's qubits begin with semiconductor nanowires, only 35 nanometers wide, roughly 2,500 times thinner than a human hair. Engineers then grow a superconducting layer only 30 atoms thick, before cooling everything close to absolute zero, where electrons pair into Cooper pairs and electricity flows with almost zero resistance. A carefully applied magnetic field pushes the material into a rare topological phase, creating exotic quantum states known as Majorana Zero Modes. They are not actual particles, but behave like them, and they become the foundation of Microsoft's entire quantum architecture. When Microsoft introduced Majorana 1 last year, it solved one problem that had challenged physicists for decades by creating a working topological qubit. Unfortunately, those qubits survived for only around 1 to 10 milliseconds, allowing roughly 10,000 quantum operations before errors became likely. Useful quantum algorithms often require millions or even billions of operations, meaning the hardware was still nowhere near practical. It proved the concept was real, but proving something works once is very different from building the future of computing. Instead of redesigning the entire chip, Microsoft changed one critical material. Majorana 1 used aluminum because it was reliable and easy to manufacture, but its superconducting energy gap was relatively small, making qubits easier to disturb. After years of research, engineers replaced aluminum with lead, whose superconducting gap is roughly 4 times larger, making unwanted quantum errors much less likely. The difficult part was growing lead with atomic precision, because even one misplaced atom could ruin the entire device. Thousands of failed attempts later, the gamble finally paid off. The result was Majorana 2, and the numbers immediately caught everyone's attention. Microsoft reported that average qubit lifetime jumped from roughly 12 milliseconds to more than 20 seconds, while some qubits remained stable for over 1 minute. That represents almost a 1,000 times improvement in just 1 year. According to Shulkoff's law, qubit lifetime typically doubles about once every year, meaning this kind of improvement would normally take close to 10 years. Independent researchers confirm these results, This could become one of the biggest breakthroughs in modern quantum computing. 20 seconds does not sound impressive until quantum physics enters the conversation. Every quantum operation takes roughly 1 microsecond, which is 1/millionth of a second. That means a qubit that survives for 20 seconds can theoretically perform around 20 million operations before an error becomes likely. Compare that to Majorana 1, which managed only about 10,000 operations. That is nearly a 2,000 times increase in useful computing time. For the first time, qubit lifetime is no longer Microsoft's biggest obstacle. The focus can finally shift from keeping qubits alive to making them actually solve useful problems. Building a chip with 4 stable qubits is impressive. Building one with thousands is where things become incredibly difficult. Every new qubit adds more wiring, more electronics, more heat, and more chances for tiny manufacturing defects to create errors. Microsoft now believes its biggest challenge is not improving qubit lifetime, but scaling this technology without losing its reliability. History shows this is often where revolutionary technologies struggle. Making one prototype is science. Manufacturing millions of them is engineering. Microsoft's confidence comes from 2 different directions. The hardware is improving much faster than expected, while quantum algorithms are becoming far more efficient. A few years ago, researchers estimated breaking RSA 2048 encryption with Shor's algorithm would require nearly 10 million physical qubits. Today, some estimates have dropped to around 600,000 qubits. The hardware requirements are shrinking, while the hardware itself keeps improving. Those 2 curves are finally moving toward each other, which is why Microsoft now believes useful quantum computers could arrive around 2029. If practical quantum computers become reality, they could transform medicine, AI, battery technology, and climate research by solving problems beyond today's supercomputers. They could also break RSA encryption, which protects banking, military communications, and the internet using Shor's algorithm. That is why governments and tech companies are already racing to develop post-quantum cryptography before quantum computers become powerful enough. As exciting as Microsoft's announcement sounds, many physicists remain cautious. A long-lasting qubit does not automatically mean a practical quantum computer. Scientists still want to see reliable quantum gates, full algorithm demonstrations, accurate error correction, and larger quantum systems working together. Microsoft's topological quantum program has also faced criticism in the past, with debates over evidence for Majorana Zero Modes. Microsoft says more experimental data is coming, and that is exactly how science should work. Big claims always invite even bigger questions. Microsoft is not alone in this race. Google, IBM, IonQ, Quantinuum, Rigetti, and PsiQuantum are all building quantum computers using different technologies, from superconducting qubits to trapped ions and photonic qubits. No one knows which approach will win because each has its own strengths and challenges. Right now, the quantum industry feels less like a single race and more like a Formula One championship, where every team believes it has the fastest machine. A 1,000 times improvement in qubit lifetime is an extraordinary achievement that could reshape the entire quantum computing timeline. It combines decades of progress in quantum physics, material science, and nanotechnology into a single breakthrough. While major engineering challenges still remain, Microsoft has solved one of the industry's biggest problems. The next question is no longer if topological quantum computing works, but how quickly it can be scaled. After more than 20 years of research, Microsoft's biggest gamble may finally be paying off. If Majorana 2 continues delivering these results, it could become one of the most important milestones in computing history and bring practical quantum computers much closer than expected. So, what do you think? Will Microsoft win the quantum race? Or will another company get there first? Share your thoughts below and subscribe for more technology breakthroughs.